All right, so last time we talked about regular languages, so it must be time to talk about non-regular languages. We're going to want to be able to show that a language is not regular. All right? And in order to do that, there are a number of techniques for doing that, but we're going to use a result called the pumping lemma. The pumping lemma is actually a pretty simple observation, so I want to illustrate the observation before we get into the technical details. So let's look at this machine here, and a person notices, of course, that it has a big loop. There we go. I've managed to avoid all of the letters. So it has a big loop. So this machine, it's easy to see. This machine, it's actually only part of the machine because I didn't want to confuse the machine with other parts. This machine, there's an A that brings you up to the loop. There's an ABB that brings you around the loop. And then there's a BC that brings you away from the loop. Okay, so there's an A that brings you up to the loop. There's an ABB that brings you around the loop. And there's a BC that brings you away from the loop. In a few minutes, we're going to call those three things alpha, beta, and gamma. So we recognize that this machine accepts A, ABB, and BC, recognizes that string. But because it does, it has to also accept A, ABB squared. That is, do ABB twice, go around the loop twice, and then BC. What we're going to call in a few minutes, alpha, beta squared, gamma. Because it just steps through the loop twice. And likewise, it also has to accept the string that steps through the loop 3 times, and etc. That is to say that looping more times will just simply pump out more strings here. Pump out more and more, oops, lost my mouse. Pump out more and more strings as you go around the loop. Pump out more and more strings as you go around the loop more and more times. Okay. Okay, so the pumping lemma. The pumping lemma says if you have a regular language, so pumping lemma is about regular languages. The pumping lemma says if you have a regular language, then there is a constant p called the pumping length of the language, where if you input a long string, where long means of length greater than or equal to p, if you input a long string, then it decomposes into 3 substrings that satisfy these conditions. Now, it does not say that every decomposition satisfies these 3 conditions. It says, but there exists a decomposition. So if you feed a long string into the machine, then there is a way to decompose, there exists a way to decompose that long string so that you can satisfy the 3 conditions. Okay? And I already talked about what that decomposition is, or at least I waved at it on the previous screen. There's alpha is the part that brings you up to the loop, beta brings you around the loop, and gamma brings you from the loop to the accepting state that you're going to end at. Okay, so not every decomposition, but there exists a decomposition. Okay, and the 3 conditions are that the first 2 components are short, namely that the total length of the string alpha and beta together, the total length of the string alpha and beta together is less than or equal to p. Beta is not empty. Beta is not empty. And furthermore, if you have to also, it has to also be acceptable to go around the string 0 many times. It has to also be acceptable to go around the string twice. It has to also be acceptable to go around the string, etc., etc. You get the idea. Okay, so the argument is really not much more than writing down in I's and J's the observation that we made on the prior slide. So this L is supposed to be a regular language, so we suppose that it's recognized by some finite state machine, M. Denote the number of states in M by P. So P could be smaller than the number of states in M, but if P if the pumping length, if you take a number that's at least equal to the number of states in M, it's sure to work. It's possible that a smaller number would work, but the number of states in M is sure to work. And you consider a string that's long in that it's longer than the length P, greater than or equal to length P. All right, so the bookkeeping on this longness is that finite state machines perform 1 transition per character. So the number of characters in the input string is equal to the number of transitions. The number of states that the machine visits is 1 more than the number of transitions. Because just think about if you have a length 1 input, you store it in some Q0, and the length 1 input brings you to some new state. It could possibly be Q0 again. But the length 1 input brings you to some state. So you visited 2 states, and again, they're not necessarily distinct states. So 1 transition, 2 states. So the number of states is always going to be non-unique states. It's always going to be 1 greater than the number of transitions. So if you have a string, sigma, that is of length greater than or equal to p, there's p plus 1 states visited, not necessarily unique states visited, some state gets repeated. Okay, so in other words, you have a loop. A loop is where you repeat at least one state. That's a loop. Okay. So we have a loop, then the rest is just a question of writing down what we wrote down in the example. So you fix the repeated state. You'll also fix the two substrings that take the machine to state Q. So in the picture here, I have the two substrings that I'm worried about here are the substring just A and the substring AABB. Just A brings you to the state Q, and AABB brings you, actually it's around the loop once, and then to the state Q. Okay, so you pick J to be minimal so that I is not equal to J, and then so what you've got is the two shortest strings, and so you're sure to have what I just a minute ago described as alpha, what brings you up to the first looping state, and alpha beta, what brings you up to the first looping state, and then around the loop exactly once. Okay, and that's exactly what it says. It defines alpha and beta to be just what we said. And again, there's a lot of I's and J's here, but it's all just detail. It's not actually an idea. And it's also, I made the observation that possibly one or both of alpha and gamma is empty. It could be that the loop starts at Q0. That could happen, so alpha could be empty. It could be that the loop ends at an accepting state, so that it could be that gamma is empty. But you can't have the beta empty because you've got to have a loop that you're going around. Okay, so clearly conditions 1 and 2 are satisfied. And then for condition 3, for the pumping part here, what we're looking at for condition 3 is that you have alpha concatenated with gamma, that is to say leave the beta out, brings you up to state Q, and then from state Q to the accepting state, and so you're accepting. Likewise, if you're going to do alpha concatenated with beta squared concatenated with gamma, this is the observation we made a minute ago, then you go up to the state Q, around the loop once, around the loop another time, and then finally off to the accepting state. So the entire string gets accepted. Okay, so really it's the observation that we made about periodicity that's going on here, and there's a lot of I's and J's and worrying about some cases, but mostly it's the observation that we made. The point of the pumping lemma is just simply that observation, that if you have a loop, then you're going to pump out accepted strings. Okay. Now, when we use the pumping lemma, we will typically use it to show that a language is not regular. So I have here 3 examples of showing that a language is not regular, and I don't like to do these things on slides because they can go by awful fast. So I'm going to do them with pen and paper. Let's see if I can make that happen. So here's my paper. There we go. Okay, there we go. Okay, so I wrote down what the examples are. Now all I got to do is find it. What the heck? Oh, here it is. Okay. So let's see. The first example on the slide says is the most important example. It says that the language is the set of all a to the n, b to the n, where n is a natural number. And what's important about this example is that it's just a rewrite of the language of balanced parens. Open paren to the n, closed paren to the n, where n is a natural number. Obviously important in computer science. You've got to worry about balancing your parens. How do you recognize balanced parens? Okay. I'm using A's and B's because parens are awkward when you write them down. And so, but nonetheless, that's the basic idea here. Very important example. So I have to use the pumping lemma to show that this language is not regular. So the way that the argument goes, the way so many arguments go in mathematics, we suppose it is regular, and we're going to end up with an impossibility. So we suppose it is regular. All right, so then fix the pumping length P. Okay. Now comes the sort of hard part, if there is a hard part. I've got to make up an appropriate sigma. The sigma has to be long, so the sigma has to be of length greater than or equal to p to make the argument work. So I'm going to consider, remember, is the word that mathematicians use for, I thought about this for a long time, and I finally hit on the right thing, and this is it. So sigma is, I'm going to take a to the p, b to the p. Okay, and of course I have to go through the argument for exactly why that works, but note that the length of sigma is greater than or equal to p. Okay, so now what do we do here? So because the length of sigma is greater than or equal to p, the pumping lemma applies. So we can decompose sigma into alpha, beta, gamma. We can decompose sigma into an alpha part, a beta part, and a gamma part, subject to the three conditions. Okay? Okay. So those three conditions, of course, are going to give me the contradiction. By condition 1, the alpha and beta part together have length less than or equal to p. The length of the alpha and beta part together is less than or equal to p. Well, look at the string. If the alpha and beta part together make a length less than or equal to p, the first p characters are all a's. So that tells you that the alpha and the beta substrings consist solely of a's. So alpha and beta consist solely of a's. By condition 2, beta is non-empty. So beta consists of at least one a. Okay. Now I'm ready for condition 3. So spelled by wrong. So by condition 3, all of these are also in the language. So let's see, alpha gamma, alpha beta squared gamma, alpha beta cubed gamma, etc. And I'm going to find a contradiction there. I could find contradiction in another place. I'm going to choose to find a contradiction here. Alpha beta squared gamma can't be a member of the language. Now, alpha beta squared gamma can't be a language. Can't be a member of the language. Because by conditions 1 and 2, when you add a beta, that's what alpha beta squared gamma is compared to sigma, and when you add a beta, you're adding a's, but no b's. Because by condition 2, compared with sigma, alpha beta squared gamma has additional a's, but no additional b's. That's not right. The language, the definition of the language is that the number of a's and the number of b's is the same. So if you take a sigma, which is in the language, necessarily has the same number of a's as b's, and you add some a's to it, but don't add any b's, you're no longer in the language. Okay, so of course that's a contradiction. That's a contradiction. So you can't have, the pumping lemma shows that you can't have you can't have a finite state machine that accepts this language. It's not possible to write a regular expression that matches that language, and etc. A person may say, well, what's wrong with the regular expression A star B star? And the answer is that matching A star B star would be something like 3 A's and 4 B's. But 3 A's and 4 B's is not a member of this language. 3 A's and 3 B's, good. 4 A's and 4 B's, good. 3 A's and 4 B's, no. Okay, so the pumping lemma, this is one, I'm going to do three, but the pumping lemma is used typically to show that things are not regular, because you assume the pumping lemma applies, as it does to all regular languages, and then you come up with some contradiction in a way like we did here. And the tricky part of the contradiction is exactly this step. You have to come up with the appropriate sigma. Now, we're going to do ones where it's not terrifically hard to come up with the appropriate sigma, but a person could still be left scratching the head saying, I'm not quite sure what to do, but that's the basic idea. Okay, two more problems. Let's go through the two more problems just to get practice. And of course, because we've gone through one, I'm going to go through the other two sort of a little more quickly. Let's see how we do. Number two. Number two is L is A to the N, B to the M, where N is M plus 1. I find that sometimes it helps people to write out a couple of strings in the language just to make sure that you have some good idea of what's in the language. So I'll write down here, how about A? How about AAB? Always one more A than there is B's. How about AAABB, etc. Okay, so just to have some feel for what's in the language. I find that to help sometimes. Okay, so in we go. So suppose it is regular. Fix a pumping length P. Consider, and I got to come up with the appropriate sigma, and what I thought to do was, much like I did in the last one, I'm going to take sigma to be A to the P plus 1, B to the P. Okay, obviously of length at least P. Okay, so now the pumping lemma applies. So gives sigma decomposes as alpha, beta, gamma. Oh, my handwriting is decaying. I'm sorry. I was trying to be good and I'm not being so good. So the pumping lemma gives that there is a decomposition. Not every decomposition, but there is a decomposition that works that satisfies the three conditions. Okay. By 1. The length of alpha beta together is less than or equal to P, so alpha and beta together consist only of A's. Obviously supposed to remind you of the previous argument. By 2, beta is not empty. So beta consists of at least one A. And again, here we go. I mean, I've done one, I've done two. Got any guesses as to what I'm doing next? By 3, all of these are also members of the language L. Alpha gamma, alpha beta squared gamma, alpha beta cubed gamma, etc. Last time I found the contradiction here, and you often have a choice about where to find the contradiction. But I'm just for variety, I'm going to find the contradiction here just to do something. So consider alpha gamma. So compared with sigma, which is alpha, beta, gamma, comma, alpha, gamma has at least one A fewer, but the same number of B's. That is to say, it's not the case that the number of A's is one more than the number of B's. So it is not true that the number of A's is one greater than the number of B's. So alpha gamma is not in the language. That's a contradiction. Okay. Ooh, I didn't quite get it on the alpha beta is not in L. Okay. Okay. One more, and just as I did this one a little more quickly and maybe a little more sloppily, I'll do the third one. There we go. Do the third one even a little more quickly. You don't want to go too quickly, but at some point you need. So the third one is the set of palindromes, and I'm going to use the same alphabet A and B. Okay, so let's see. I'm looking for the set of palindromes. So 3. You let L be the set of palindromes. It's not a very good notation. Okay, so you know, just to remind a person, I do find it's a bit of a help. So how about something like A, B, B, A, and I guess just A, and just B, and B, A, B, and etc. Okay, so I'm of course going to apply the pumping lemma, and I'm illustrating what's happening here. So we suppose it's regular. And let the pumping length be P. Okay, and you consider. Now this is what I was talking about earlier. Every once in a while you run into a sigma where you got to do a little head scratching. I scratched my head for a few minutes and I decided to look at A to the P, B, A to the P. That's a palindrome, all right. You got to pick your sigma to be a member of L. That's a palindrome, all right, and I think I can get the argument to go through. By the pumping lemma, sigma D, there is a decomposition of sigma into 3 substrings, alpha, beta, gamma, that satisfy 1 through 3. And by 1, alpha and beta together consist only of A's. By 2, beta consists of at least one A. Beta is not empty, so beta consists of at least one A. And by 3. By 3, all of these are members of L. So alpha gamma, alpha beta squared gamma, alpha beta cubed gamma, etc. Now I didn't write alpha beta gamma because we know that's a member of L. I'm not going to find the contradiction there. It's a member of L because there it is. I chose it to be a member of L. So I got to find the contradiction in one of these other ones, and you can a lot of times you find it, you know, in one of the first two. So just to pick one, I'll pick the first one again. I could pick this one here, but I pick this one here. Okay, so consider alpha gamma compared with sigma it has at least one A removed from the initial part. One A removed from the initial part. But no A's are removed from the final part. No A's are removed from the part after B. So it's not a palindrome. And of course, that's a contradiction. That contradicts the pumping lemma. That is a contradiction. Okay, very good. Okay, so three cases, and you should try some of the ones in the homework because they're very similar to these. All right, very good.